Dear students, I am Hiba Haq, lecturer of physics from Government Degree College, Malir, Cantt, Karachi. So this is my second lecture on kinetic theory and the ideal gas, which is the topic from intermediate Sindh textbook. Okay, so this is a small review of my previous lecture. In my previous lecture, I explained what is kinetic theory of gases, and I discuss the basic assumption used to construct a molecular model of gases. And on basis of these assumptions, I derive the expression for the pressure of gas molecules, and this is P is equals to 1 upon 3 rho V square bar, where rho is the density of gas molecules and V square bar is the average square velocity of gas molecules. So note that when I derive this relation, I assume that molecule-molecule interaction is negligible. But if the molecule-molecule collision included, the expression will remain unchanged. Today I am going to explain kinetic interpretation of the temperature and verification of gas laws using kinetic theory of gases. So let's start with kinetic interpretation of temperature. First of all, we need to understand what is temperature. A temperature is that property of a thermodynamic system which determines whether or not it will be in thermal equilibrium with other systems. When two or more systems are in thermal equilibrium, they are said to have the same temperature. So here is a figure in which there are two bodies at different temperature. So when these bodies are placed in thermal contact with each other, heat will flow from hot body to cold body till the temperature of both bodies become same with respect to the surrounding. So this state is known as thermal equilibrium state. Now, scales of temperature. We have three scales: Kelvin scale, Celsius scale, Fahrenheit scale. So if we talk about Fahrenheit scale, boiling point of water will be 212 degree Fahrenheit. Human body temperature is 96.6 degree Fahrenheit. Freezing point of water or melting point of ice is 32 degree Fahrenheit, and absolute zero will be minus 459.67, which is approximately equal to minus 460 degree Fahrenheit. Now, if we talk about Celsius scale, boiling point of water in Celsius scale is 100 degree centigrade. Human body temperature is 37 degree centigrade. Freezing point of water or melting point of ice is 0 at 0 degree centigrade, and absolute zero will be at minus 273.15 degree centigrade, or just minus 273 if you round off it, minus 273 degree centigrade. Now, the SI unit of temperature is Kelvin. If we talk about Kelvin scale, the boiling point of water in Kelvin scale is at 373.15 Kelvin. Human body temperature is at 310.15 Kelvin, and freezing point of water or melting point of ice is at 273.15 Kelvin, and we all know that absolute zero is actually 0 Kelvin. Okay, now let's talk about conversion of scales of temperature. For that, you need to memorize this table. In this table, we have a temperature scale and the lower fixed point or melting point of ice, then upper fixed point, boiling point of water, or total number of interval between lower fixed point and upper fixed point. So if we talk about Celsius scale, the lower fixed point or melting point of ice is at 0 degree centigrade, upper fixed point or boiling point of water is at 100 degree centigrade, and the total number of interval between lower fixed point and upper fixed point is 100. Now, Fahrenheit degree scale, lower fixed point or melting point of ice is at 32 degree Fahrenheit, upper fixed point or boiling point of water is at 212 degree Fahrenheit, and total number of interval between upper fixed point and lower fixed point is 180. Now, if we talk about Kelvin scale, lower fixed point is at 273 Kelvin, upper fixed point is at 373 Kelvin, and total number of interval between upper fixed point and lower fixed point is 100. So if you memorize this table, you can easily convert a given temperature scale into your desired temperature scale. And we the formula we used is temperature on one scale minus lower fixed point of that scale divided by number of interval between two fixed points, and this should be equal to temperature on other scale minus lower fixed point divided by number of interval between two fixed points. So here is an example. Convert 300 Kelvin into Fahrenheit scale. Using the formula, we have one scale that is Kelvin, and we have to convert it into a degree Fahrenheit or Fahrenheit scale. So for that, temperature on one scale, that is 300 Kelvin, minus lower fixed point of that scale, that is 273, divided by total number of interval between upper fixed point and lower fixed point, that is 100, is equal to degree Fahrenheit temperature on second scale minus lower fixed point of that scale, that is 32 degree, divided by 180. Or I can write it as degree Fahrenheit minus 32 degree upon 18 is equal to 27 upon 10. So if you minus 273 from 300, you get 27. Or further, degree Fahrenheit minus 32 degrees equals to 27 into 18 upon 10. So if you calculate it, it will be 48.6. And degree Fahrenheit is equal to 48.6 plus 32. So degree Fahrenheit is equal to 80.6 degree. So okay, after understanding the concept of temperature and scales of temperature, come back to our topic. We all know that pressure of an ideal gas using kinetic theory of gases is P is equals to 1 upon 3 rho V square bar. I mark it as equation number 8, where rho is the density of gas molecules, and we all know that rho is equals to mass per unit volume. So total mass of gas molecule divided by volume of a cubic vessel. Or I can write it as rho is equals to N, capital N, which is total number of molecules, into small m, mass of one molecule, divided by V. Now what I do, I just put the value of rho in equation number 8. Equation number 8 will become 1 N, capital N into small m, divided by 3 into capital V into small v square bar. So after rearranging it, rearranging the previous equation, we get PV is equals to 1 upon 3 capital N into M into V square bar. I mark it as equation number 9. Now I'm going to introduce general gas law. We all know that general gas law states and that PV is equals to nRT, where P is the pressure of exerted by gas molecules, V is the volume of a vessel in which gas molecules are confined, N is the number of moles, that is total number of molecules divided by Avogadro's number. We all know that Avogadro's number is 6.022 into 10 raised to the power 23 molecules per mole. Then T is the temperature of gas molecules in Kelvin, and last capital R is the universal gas constant, and its value is 8.314 joules per mole per Kelvin. Okay, now we compare equation number 9 and 10. We get N into RT is equals to 1 upon 3 into capital N into M V square bar. I'm going to just rearrange this equation. MV square bar will be equal to 3 into small n into RT divided by capital N. Now multiply divide this equation by 2 on both sides. So 3 into small n into r into t divided by 2n is equals to half mv square bar. I mark it as equation number 11. So this half mv square bar is the average translational kinetic energy per molecule. Now we put the value of number of moles. This is capital N, total number of molecule divided by Avogadro's number in equation 11. Equation 11 number 11 becomes 3 upon 2 into capital N into R into T divided by Na into small n is equals to half mv square bar. So this n and this n will cancel. Equation reduces to 3 upon 2 into RT divided by Na is equals to half mv square bar. So this R is a general gas law, general gas constant, or universal gas constant, and this Na is Avogadro's number. We know the value of both quantities. So what we do, we just put the value of R and Na. This is 8.314 joules per mole per Kelvin, and Avogadro's number is 6.022 into 10 raised to the power 23 molecules per mole. So this per mole and this per mole will cancel. If we divide, we get 1.38 exponential minus 23 joules per molecules into Kelvin. So this is a Boltzmann constant. We represent it with a small k. So now our equation will be 3 upon 2 kt is equals to half mv square bar. So I mark it as equation number 12. So in this equation, half mv square is the average translational kinetic energy per gas molecule, and then T is the temperature of gas molecules. We measure it in Kelvin. So 3 upon 2 K is constant. So if we remove constant, we get proportional sign. So equation number 12 will become half mv square bar proportional to T. So this shows that the average kinetic energy per molecule of an ideal gas is directly proportional to temperature of a gas molecule. Therefore, it depends only on the temperature and not on the pressure or volume. This equation defines temperature in terms of mechanical energy, or using this relationship, we can say that temperature is the measure of kinetic energy of all gas molecules. Okay, after a brief discussion on the kinetic interpretation of the temperature, I am going to explain that how can we verify the gas laws using kinetic theory of gases. So first of all, we try to understand what is gas law. The behavior of gas can be described with the help of 4 variables. These variables are volume, temperature, pressure, and mass respectively. A gas law deals with the relationship between any 2 of these variables while keeping the other constant. So we have Boyle's law, Charles' law, and general gas law. Now, a gas that obeys these laws is known as ideal gas. We have nitrogen, oxygen, hydrogen, and noble gases, and heavier gases like carbon dioxide. We can treat these gases as an ideal gas within a reasonable tolerance. So the first verification is of Boyle's law. For that, we need to understand what Boyle's law states. So Boyle's law states that the volume of a given mass of an ideal gas is inversely proportional to the pressure applied when temperature of a gas is kept constant. So if V be the volume of a gas and P be the amount of pressure applied or they exert, V is inversely proportional to 1 upon P, and if T, that is temperature and mass of gas, are constants. So if we remove proportional sign, we get a constant. We mark it as K. So or I can write it as PV is equals to small k, which is constant, if T and M are constant. So this law can be stated in other way as, for a fixed mass of a gas at constant temperature, the product of pressure and volume is constant. Okay, so here is a gas fill cylinder with a piston, a movable piston. This gas is at a constant temperature, that is 300 Kelvin, and we freeze the mass of the gas. So now if we change the pressure on the piston, the volume of gas changes. For example, if you increase the pressure, the gas compresses and volume decreases, and vice versa. So if we draw a graph between pressure of a gas and volume, it is a hyperbolic curve which shows that if you increase the pressure, a volume of a gas decreases. Okay, now I'm going to verify Boyle's law using kinetic theory of gases. For that, we know that pressure of an ideal gas using kinetic theory of gases is P is equals to 1 upon 3 rho V square bar, where rho is the density, which is equal to mass per unit volume. So what we do, I just put the value of rho in equation, in above equation. Equation changes to 1 upon 3 into capital M upon V into V square bar. So or PV is equals to small capital N into small m V square bar upon 3, where capital N is the number of molecules and small m is the mass of one molecule. I mark it as equation number 13. Now from equation 12, we know that half mv square bar is equals to 3 upon 2 kt. I'm going to find the value of v square from this equation, which is v square is equals to this 2 and 2 will cancel and m will be go here, 3 kt upon capital M. So what we do, I do the put the value of v square bar in equation number 13. Equation 13 changes to PV is equals to N into M upon 3 and V square bar is equal to 3 kt upon M. So this M and this M will cancel, and PV is equals to N dot K dot K. Now if we talk about Boyle's law, the condition for Boyle's law is that temperature of a gas is kept constant. So if the temperature of a gas is kept constant, this N is the number of total number of gas molecule which is constant, and K is a Boltzmann constant. So this product will become constant. So this is PV is equals to constant, which is a relation for Boyle's law, that if the temperature of a gas is kept constant, the product of pressure of a gas and volume of a gas is kept constant. Okay, now second law is Charles' law. First we will discuss the statement of Charles' law. Charles' law states that volume of a given mass of an ideal gas is directly proportional to its absolute temperature if pressure of a gas is kept constant. So if V be the volume of an ideal gas and T be the temperature of the gas, then according to this law, V is directly proportional to T. So this only happen when P and N, that is pressure and mass of an ideal gas, are constant. So if we remove the sign of proportionality, we get a constant, same like we did in Boyle's law. V is equals to K into T, or we can say that V upon K is equals to constant, where if P and N are constant. The second statement of this law is that ratio of volume of a given mass of an ideal gas to its absolute temperature is constant if pressure of a gas is kept constant. So again, if a gas is filled in a cylinder which is covered by a movable piston, now if we fix the pressure, that is 1.5 Newton per meter square of a gas, and let's suppose the mass of a gas is also constant. Now if you increase the temperature, the gas will expand and its volume increases, and vice versa. If you decrease the temperature of a gas will compress and its volume decreases. So if you draw a graph between volume and temperature, such that temperature of a gas is along x-axis and volume is on y-axis, we get a straight line. So for the verification of Charles' law using kinetic theory of gases, this expression which I already derived, that is PV is equals to n dot k dot t, where n is the number of molecules, total number of gas molecule, k is Boltzmann constant, and t is the temperature of a gas. So if I rewrite this equation, then V upon T is equals to n dot K upon P. Now now if we talk about Charles' law, the ratio of volume to temperature is constant if the pressure of a gas is constant. So if we take P as constant, this ratio will become constant, and we get V upon T is equals to constant, which is the relationship for Charles' law. Okay, now for the verification of general gas law. General gas law is simply a combination of Charles' law and Boyle's law. It is a single relation into which Boyle's and Charles' law are combined, and is also known as an ideal gas law. So this law, according to this law, pressure into volume is equals to nRT. So same pressure, P is the pressure of a gas, V is the volume of a vessel in which gas is confined, N is the number of mole, T is temperature of a gas in Kelvin, and R is the universal gas constant. Okay, so for verification of gas law, general gas law, I am using this relation again, that PV is equals to n dot k dot t. In this expression, K is Boltzmann constant, which is the ratio of universal gas constant and Avogadro's number. So just put the value of K in above equation. We get PV is equals to n dot t dot r upon Na, or PV is equals to n upon Na dot r dot t. Now this total number of molecules divided by Avogadro's number is a number of mole, so the relationship become PV is equals to nRT. So this is all about the verification of general gas law, Boyle's law, and Charles' law using kinetic theory of gases. I hope you understand what is kinetic theory of gases. Then the interpretation of pressure on kinetic theory of gases, and kinetic interpretation of the temperature, and at the end how we can verify gas laws using kinetic theory of gases. So I will end my lecture with these words, that we learn more in crisis than in comfort. If you have any question, please feel free to ask. I try my best to answer them. So thank you. Take care. God bless you.